work. So now, you take a look at the problem. If the electric field is in this direction, right? And they have a point charge Q, it gives you a value for it.
Q, 2 nanocoulombs.
All right, so Q is equal to 2 nanocoulombs. Now, please watch this. The location -5, 10, 2 is at a height of 2. So -5 would be somewhere down here, 2 would be over here, 10 would be over here, and then 2 would be up this way. So it's at a height, a distance from the actual ground plane of 2 meters. And then it's gonna move down to the ground plane, or it's gonna move actually to where the charge is. And the reason is, this is the X, Y, and Z coordinates. X, Y, Z coordinates right here. So it's gonna go from 2 to 0. These coordinates, X and Y, have no bearing on the problem, because if the electric field's in the vertical direction, the force on this will be QE. Do you agree with that? So the electrical force is pushing this way. That means with an external force comes in, it's gonna have to push against that. You follow me on this? Therefore, the work it does is gonna be the integral of, of Q times E, and if E is just rho S over 2 epsilon naught, and it is in the positive, now think about this, that's in the positive AZ direction. The force we apply is gonna be in the negative AZ to push against that. Does that make sense to everybody? So what we're gonna do is put minus AZ here. Now it's dotted into the differential length. I'm gonna write the whole differential one time. The differential length in Cartesian coordinates was dx ax plus dy ay plus dz az. I'm only doing this once. And by the way, did you see that I put the differentials up there and I showed you the coordinate systems? Now we go from point. By the way, when we do this, you'll notice when we go ahead and do the dot product here before I put in the limits, what do you see happening? It's real important. What is az dot ax? 0. So just erase this. az dot ay? 0. Erase it. I want to do it one time. But az dot az is 1. So now I get rid of that, and it's 1, but it is a negative, right? There is a negative sign there because the force we're using is pushing downward, correct, class? Now, since this is only going to be dz, the only thing I care about is the difference in the z coordinates. The x and the y coordinates have no bearing on this problem whatsoever. You follow me, everyone? So z starts at 2, and it goes to 0. That means the work I do will be the integral of really minus q rho s over 2 epsilon naught. And then when I integrate dz, I get z, and z is evaluated from 0 minus 2. Or really, it's going to be equal to 2q rho s over 2 epsilon naught. Or simply, it's q rho s over epsilon naught. And that would be the amount of work. And I don't know, what does that come down to? That's, q is 2 nanocoulombs, right? So it's 2 times 10 to the minus 9. And rho s is 100 nanocoulombs, so that's 10 to the minus 7. And then it's over epsilon naught, which is 1 over 36 pi times 10 to the minus 9. This is one way of writing it. You could put 8.854 times 10 to the minus 12, but 1 over 36 pi it makes it easier to do the math on this one. So I can see that 10 to the minus 9s cancel right off the bat. Then I have 36 pi here, 1 over 36 pi. Up top is 72 pi times 10 to the minus 7 joules of work. And if you want to give me a number for that, you can, and we'll check the answer. I think this is right. Is it right in the book, do you know? Did you do this, Josh?
Yeah.
Is it the right answer?
I don't know what that is. 79 microjoules.
All right, can you just check? 79 micro, okay, that could be. 72 pi times 10 to the minus 7, what did you do? Just 72 times pi. Anyone? Going once, going twice.
And that came out as
What's that?
23, that's 23.
Well, what did I mess up? It is two nanocoulombs, right?
Mm-hmm.
Just do this calculation, Q rho S over epsilon naught, unless I've done something wrong here. 100,
The direction it's in, the force is in the y direction, and so
what, isn't it Z? It's in the XY plane?
it's in the xz plane.
Oh, boy. My bad, it's in the XZ plane, then
Yeah.
it's, then, hold on for 1 second. We gotta, I don't know why. I thought it was in the XY. If it's in the XZ plane, that's different. Then I draw it right, first of all. So actually, if this is now the charge density is in the XZ plane, did you say?
Mhm.
In your books?
Yep.
All right. With that in mind, it's, maybe I'm wrong. So this is gonna be rho S, and that's 100 nanocoulombs per meter squared. And then, give me the position again, point, the first point was
Is-
P, right?
Yep, -5, 10, and 2.
And M?
Is 2, 3, and 0.
All right. And then if we have this, it changes things. That means the E field on this side is equal to simply rho S over 2 epsilon naught in the AY direction. And the E field on this side would be equal to rho S over 2 epsilon naught in the minus AY direction. I'm just putting it back there to get some clarity. The charge equal to 2 nanocoulombs, or, yeah, it's 2 nanocoulombs. So it moves from point P to M. And so now it's moving, the only thing I'm worried about is the change in the Y coordinates. So it goes from 10 to 3. I know that the other coordinates, because you see the direction of the E field? It's in the Y direction. That means only the difference in the Y coordinates is gonna have a bearing on the actual amount of work or energy that's, that it takes to move this thing. So if we take a look at this, I start at 10, I go to 3. Y equals 10 is out here. Y equals 3 is here. And the electric field's pointing that way. QE would be in this direction, so the force right here would be QE, and it would be in that direction. That means externally, if I move this thing, right, I'm gonna have to push it. It's not gonna go by its own, right? That means it's positive work I'm gonna do. So this one breaks down to be simply the force, which is Q times rho E, times E, rho S over 2 epsilon naught in the AY direction. My force is gonna be in the negative direction, negative AY, because I'm out here and I'm pushing this way, going in the minus AY direction. And then I'm just gonna put DY, AY here because we know the AX and the AZ differentials will dot to 0. So I'm just leaving it as DY. And it starts at 10 and it goes to 3. And this would be the amount of work. And that means that it's actually gonna be Q rho S over 2 epsilon naught, and then it's going to be minus 3 minus 10, or really 10 minus 3, or 7. So this should be the answer. It should be Q is going to be equal to, I got 2 nanocoulombs times 10 to the minus 9 times rho S is going to be equal to 10 to the minus 7 over 2, and then it's going to be 1 over 36 pi times 10 to the minus 9. And then it's gonna be times 10 minus 3 is 7, and that should be your answer. So 10 to the minus 9's cancel, 2's cancel, and I got 36 pi times 7 times 7 times 10 to the minus 7. That's the answer, I hope. Is that it? Does it come out? Okay. So what's it, 790 did you say?
79.
79 microjoules, right? All right, I wanted to do that. Now, the next one I want to do is problem 430, or I'm sorry, problem 343. And that has an equation. This is one I didn't cover in class, but I want to make sure you get it. This one, they give you an equation for a surface. Just call it S. And they say S is stipulated by 2x plus 4y squared, 2x plus 4y squared, plus the natural log of z, all equals a constant, which is 12. Now, you can't envision this, but I'm going to tell you this is a surface. MATLAB, I think, has the ability to render this, but this is a surface, and it's tough to get a handle on it. Normally, what you do with a problem like this, if you wanted to sketch this, you would set one value constant, like suppose you set z equal to 1, all right? Well, the log of 1 is 0. Do you agree with me? Now, if you do that, then you can sketch 2x plus 4y squared equal 12, and you can get the actual, it's a parabola. It looks like a parabola, right? Then you change the value of z to say 2 or 3 or 4, and you can get sketches. You have contours, so you're basically doing. But that's not part of what I'm worried about. What we want to do is find a unit normal, is what he asked for, right? So write this down. If you want a normal vector to any plane that's defined this way, what you have to do is simply set this whole thing equal to 0. So it would be minus 12 equals 0. You don't have to do it this way, but this is the way it's usually done. And you don't have to actually set it to 0. You can just call it a function f. Just do it this way. And then you can say a unit normal to this surface, and this always works, is going to be the gradient of f over the magnitude of the gradient of f. It's a unit vector. One of the questions you should have is how do you know whether that should be plus or minus? It has to do with side of the actual surface you're on. Now, because that surface isn't one obvious, what it is a closed surface, but it's not an obvious one. The unit normal will be outward from the surface, and I'm just going to say that. It'll be outward from the surface, unless there's a reason, some reason that prevents that. Let me go through and do this. So first, what is the gradient of f? Remember how to take a gradient? In the back of the book. This is Cartesian coordinates, right? So the gradient of f is just the derivative of f with respect to x, ax, plus the derivative of f with respect to y, ay, plus the derivative of f with respect to z, az. That's all it is. So that means this, if I come up here, and I can say a normal is equal to the gradient of f over the magnitude of the gradient of f. Here it becomes, well, what is the gradient of this? Take a derivative of this with respect to x, you get what? 2ax. Derivative with respect to y?
8y.
8y, and that's in the ay direction. And the derivative of this with respect to z? 1 over z az, right? Derivative of natural log. So that's the a normal, that's the gradient. What's the magnitude of this? Well, it'll be the square root of 2 squared, or 4, plus 60, what would be 64y squared, right? Plus 1 over z squared. Do y'all agree with me? So that's going to be the magnitude. Now, at a given point, you can evaluate that. Right? Do they give you a point they wanted to evaluate that?
Mm-hmm.
They do? What is it?
3, 2, 1.
Yeah, 3, 2, 1.
All right, that means a normal at 3, 2, 1 would be 2ax plus 16ay plus az, all over the square root of, that's going to be 4 plus 16 squared plus 1. So what is that? It's 196 and 4 is 200, 201. Is that what that comes to?
261.
261. Yeah, that's 256, you're right. It's 261. This is 261. and that would be a normal. I don't know what the square root of 261 is, but it doesn't really matter. You can do this. That's what a normal is. What's the next part of that problem?
That was all.
Just a normal? Well, that's how you get a unit normal to a surface. This comes in handy later on. Since he didn't specify if you want the unit normal with respect to one direction or the other, really what you should do is this. Put plus or minus. It depends which way you need the unit normal. Generally, the default is positive. All right, that's that problem. Next, we're going to talk about, I'm going to do 344. We can do any, by the way, if you walked in late, if you have any problems you want me to do from the homework you have questions about, ask now. Which,
Yeah, I think it was 3.39, which says given D equals 3AX plus 2XY AY.
X, Y, A, Y, go ahead.
Plus 8X squared Y cubed AZ. Determine the charge density at the point 111.
Okay. How do we do, if you're given a D field and you want the charge density, that's rho V, right? What do you do? Anyone?
Do divergence.
Say again?
Take the divergence.
That's right. Divergence of the D field is equal to rho V. And that's called what? There's a law. Anyone? Very famous man. What's the law? Gauss's law. It's the point form of Gauss's law, right? Right? So, having said that, what is divergence of D? Well, rho V would be equal to the derivative of dx with respect to x plus the derivative of dy with respect to y plus the derivative of dz with respect to z. That means rho V equals, take a derivative of this right here. This is dx, by the way. It's the coefficient of ax is dx. Derivative of that is 0, isn't it, class? Then derivative of y would be 2x, right? And the derivative of z with respect to z is what? It's 0, right? So it's 2x, and it's evaluated at 111. That means rho V is just 2. And the units would be coulombs per meter cubed. Is that the answer in the book?
Yeah, and then there's a part 2.
Go ahead.
And 3. So it says find the flux through the surface of a cube with 0 is less than or equal to x, which is less than or equal to 2. And then y is between the same coordinates, and so is z.
So we have x, y, and z, and give me the dimensions again.
They're all between 0 and 2 meters.
All right, x, y, and z,
Mm-hmm.
all positive?
Yep.
All right, then I'm gonna do it this way. You can integrate the flux, this D field, over the 6 surfaces of the cube, right? And when you do the dot product with any surface, you're gonna get rid of 2 of the 3 of these terms that do the integration. However, my gut feel tells me just integrating that over the volume will be a lot easier. Volume charge density integrated over the volume is the amount of charge. And when he wants the flux, the word flux over any closed surface is the amount of charge enclosed. That's Gauss's law. So the only thing we do is we say the charge Q is equal to the integral. It's a triple integral of rho V, which is 2x, right? So it'd be 2x, then it's dx, dy, dz. Does everybody agree with that? Charge density, differential volume is dx, dy, dz. Well, where does x go from, class?
It goes from 0 to 2.
Y
0 to 2.
and z.
0 to 2.
All right, that means the charge is simply going to be equal to 2. Well, when I integrate x dx, I get x squared over 2. Evaluated from 0 to 2 is just 2 squared, right? I integrate dy from 0 to 2, I get 2. Integrate dz from 0 to 2, I get 2. And you can see what I have here is what? 4 times 4, or 16 coulombs, if the units are coulomb.
For the right?
What?
That's for the total. Okay, oh yeah.
that it?
Yeah.
Now, if you do it all over, if you take this and integrate over each surface, it's gonna take a little more time.
As I said, it asks you for the left side and the right side.
All right, well, do the volumetric one and skip, because it will come out the same.
Well, because I was confused, because the left one comes out to be 0, and the right one comes out to be 16. So that's where I was
No,
confused.
no, it's wrong, they're the same. What were you shaking?
I was saying, no, like,
It's an impossibility, it's the integral of d
Yeah,
dot
that's why I was
ds.
confused, because I thought they would just be the same. But on the answer here, it says right 16, and left 0.
No, he's going through the individual surfaces here.
Yeah.
like you add them all over.
Yeah, it'll be the same.
Yeah, no, yeah. I was just wondering why the left one was 0, right?
It's just one of them's 0, just one of them. Only, one of the surfaces is 0, but all the surfaces add up to the same value.
Okay.
All right,
Those ones cancel all their statements. Left over 16.
that's that one. Any other one? We're gonna do one with a gradient in a second. All right, next, I wanna do, uh, 344. Now, this is the easy one of gradient operators, but it has a voltage V defined as x plus y squared z. That's a scalar operator. It's in Cartesian. And they want to know the E field, right? So what's the relationship between voltage and electric field for electrostatics?
Negative integral.
Not integral, minus the gradient of V, right? Remember this, that is the differential form. The integral form is V between B and A is equal to minus the integral, right? From A to B of E dot dl. That's voltage. If you have voltage, you want E field, you do the gradient operator. And remember that voltage that's given there is with respect to some ground point. And the ground in this case, V equals 0, would be x, y, z equals 0. Just look at that. Right? All right, now, what is the gradient operator? It's minus dv dx ax, right? Minus dv dy ay, minus dv dz az. Do you all agree with me? So this is a straight up operation. You can say the E field here would be derivative with respect to x is what of that class? Right, so it's minus ax, minus what's the derivative with respect to y?
2. Just 2.
2yz, right? 2yz ay. Remember that. You can't be casual about this or sloppy. And what's the z operation? Minus derivative with respect to z class? Y squared. Y squared. Az. Are you with me? That's it. And you can evaluate E anywhere you want. Okay? There are two others, one given in cylindrical, the other given in spherical. They want the gradient operator on, right? And I would give you the definition of those gradients. I won't give you this one in Cartesian. You have to know that. You have to know the divergence in Cartesian as well. All right. Next, after that, now we're gonna do I'm gonna show you how you can use voltage to get the E field for any charge distribution. But first I'm gonna say something. Anytime you have a finite amount of charge you're dealing with, usually the place where you consider zero potential is at infinity. You assume if you're at infinity, that's where 0 volts is. Everything else is measured with respect to infinity, being 0. So then you can say this, if that is the case, if the 0 volts is at infinity, then you can say the differential voltage, and this works for every finite amount of charge. The differential voltage can be defined as simply the differential charge divided by 4 pi epsilon naught r. You'll notice r is the radial distance between the actual, and maybe a little, let's say this is a chunk of charge dq, this is the distance away, and this is the voltage I'm talking about. It's only a function of the distance from that point. And I'm gonna try to explain it the way I'd like it explained to me if I was sitting in your seat. Now, having said that, I'm going to do a classic problem. First one I'm going to do is the ring. If we have, just think about this. Before, if we had a loop, and we had a line charge density, rho L on that loop, and it's at a radius A, okay? And I want the voltage at a point Z. Does everybody realize that's a finite amount of charge, right? It's just a ring. There's a certain amount of charge density, and the total charge density would be rho L times the perimeter of that loop, or the circumference of this circle. All right, now, when I do this, I'm going to say that for this problem, dV here would be equal to, and what you have to do is take a little chunk of this thing. So if you think about this, this has an extent d theta, right? But it's times a d theta for the length. That would be equal to dl. You all agree with that? And then dq, the differential charge there, dq would be equal to a d phi, or differential length, times the charge density, rho L. So I can say here, I have a times d phi times rho L, that's the differential amount of charge over 4 pi epsilon naught. And now I put r down. I'm going to say one thing. This is the distance you worry about, that's z. And we're going to take the gradient operator with respect to z. This distance is fixed, does not change, but we want the voltage anywhere on the z-axis, correct? So now I put down, this is going to be the square root of z squared plus a squared to the 1/2 power. Does everybody agree that that is the radial distance between this point here and this point? That would be r, correct? It's the distance. Do you agree with me, everyone? Now, when we go ahead and we find voltage, what do? Well, we take the integral of dV to get V over the region. Well, here, this is how easy it is. When I take the integral of rho L A d phi over 4 pi epsilon naught z squared plus a squared to the 1/2 power, where do I go in terms of phi? From where to where?
0 to 2 pi.
All the way around the circle, 0 to 2 pi. Make sure you know that. 0 to 2 pi. So that means my voltage, now look at this. Is anything in here except the differential a function of phi? Nothing, right? What does that mean? It means when you do the integral, you're just taking d phi from 0 to 2 pi and multiplying it by 2 pi. There's a 4 pi, it cancels. So this is going to be simply rho L A, right, over, or times 2 pi, right here, times 2 pi, divided by 4 pi epsilon naught, and then it's z squared plus a squared to the 1/2 power. And that is my differential, that is the voltage. It's not really a good one either. This one's better. Finally, just to clean it up a bit, this means it's going to be equal to rho L A over 2 epsilon naught z squared plus a squared, z squared plus a squared to the 1/2 power. Now that's V, right? Remember, A is a constant. So what is the E field? The E field anywhere on the z-axis at any point z? Well, it's the gradient of that, right? Minus the gradient of that, correct? So it's minus the gradient of V. And since this is V right here, does everybody agree with me there? What's the gradient going to be? Well, I'll take the constants out in front. It's minus rho L A over 2 epsilon naught. Now, When you think of gradient with respect to rho, remember A is a constant, it's 0, isn't it? Take a derivative of this with respect to rho. If A is a constant, it is 0. Do you agree with me? Now Z is allowed to fluctuate, it's up and down the Z-axis. Then you take the derivative with respect to Z. You could do it with X, Y, and Z too. Derivative with respect to X would be 0, derivative with respect to Y would be 0. And the derivative with respect to Z is what? It's going to be what? That's like Z squared plus A squared to the minus 1/2 power, isn't it? So it would become minus 1/2, right? And then it would be Z squared plus A squared to the minus what? 3/2, correct? Derivative, right? 1/2 to 3/2, correct? And then, no, not minus, it's plus 3/2 there. 3/2 power. And then it would be the derivative of this, Z squared plus A squared with respect to Z would be 2 times Z, right? And that means the value I would get, therefore, would be minus rho L A times Z over 2 epsilon naught, this 2's cancel, 2 epsilon naught times Z squared plus A squared to the 3/2 power, and it would be in the AZ direction. I didn't put down AZ, but it's in the AZ direction. And this would be the electric field. Do you remember when we calculated? There's 2 minus signs, so this becomes a plus actually. Do you all remember calculating that, class? Well, that's how you get it, just using the definition of voltage, the differential voltage, and then doing a gradient. You're gonna find this way is a lot easier a lot of times, calculating the E field, than doing a vector integral, where you have 3 components to integrate over. Just calculating the scalar V and then doing the gradient is much easier, usually. And to be frank, that's the way a lot of numerical programs calculate it too. All right, so now that's for a single loop, right? Now here's like a typical test question that I give. Let me erase this. Leave that up there and remember this right here. So now, suppose I don't have that. Suppose I have this. Actually, remember this. This is what we want. That's the voltage on the Z-axis at any point Z. Now suppose I have this is my deal. I have now a loop right here. And the loop has a radius, I shouldn't say a loop, a plate, a radius of A, but everywhere on the loop I have a charge density rho S. So now I don't have just a, so there's charge everywhere here. Right? And now I want to know, first what VZ is at any point Z, and then I also want to know what E is on the Z-axis. I want to know those 2 things. This is a great problem. This is the kind of stuff I ask on tests. So now what you have to do is this. Take a look at this. I know I could say I have a loop out here at some radius, and I'll just use the term rho here. And I'm going to try to draw this loop so it looks like this, right? And the loop has got some thickness to it. So I'm going to say this loop has a thickness right here of d rho. It's at a distance rho, right? Coming out to this distance rho. And the radius of this loop will make A. So here's the way I do this problem. I say that I know what the differential voltage is from that loop of thickness d rho, because I just got it over there, right? So what do I have to do? I can say, and I'll do it here, that the differential voltage on the z-axis would be equal to the differential charge. Well, what is that differential charge? It's all of that charge, isn't it, right there? So how much charge? It would be what? It would be 2 pi rho. That's the circumference of this loop, isn't it? Right there at a radius rho. And it's times the thickness, d rho. So that's going to be the surface area. And then I have to multiply it by rho s. So that times rho s this is like dq. I only take that and I divide it by the distance from this point to this point. And this is at a height z. So we can say that this has got a height z. And I know this radial distance r would be equal to the square root of z squared plus rho squared. Y'all agree with me there? Right. So now I put that down. So it's going to be this divided by the square root, divided by 4 pi epsilon naught times the square root of z squared plus rho squared. Just write that down. Do you all agree that that's the differential voltage from a differentially thick piece of that ring? Agree, class? All right, what's the total voltage? Well, the voltage would be what? The integral, it's going to be an integration in rho from 0 to a, correct? And that would be equal to, well, the 4 pi, 2 pi business cancel, and I get 1/2, 1 over 2 epsilon naught, and then up top I get rho d rho. I can take rho s out in front, and I have z squared plus rho squared here. You all agree with me? Now for this integration, this is really going to be v is equal to rho s over 2 epsilon naught times the integration from 0 to a of rho d rho over z squared plus rho squared to the 1/2 power. This should be 1/2 down here, rho squared to the 1/2 power. So I'll do that integral here. And if I have the integration of rho d rho over rho squared plus z squared to the 1/2 power, now I can make u squared equal to just rho squared plus z squared, right? And then, since it's d rho, du times u times 2u du is equal to 2 rho d rho plus 0, because we're doing a differential. The integration is only in rho. Do you all agree with me there? And that means this integral here would be really the integration. Rho d rho is really u du over, and then I have rho squared plus z squared, which is u squared, right? But u squared to the 1/2 is just u, is it not, class? And where does u go from? Well, since I've defined u as rho squared plus z squared, when rho is 0, it starts at z squared, correct? And then it goes to, all the way up to, here is going to be when when rho is equal to a, then it goes to a squared plus z squared. Do y'all agree with me there? And that would be equal to, well, what is that going to be? That's actually, well, u over u cancels, so I just get what? Actually, this goes to the square root of that. That's z and the square root of this. See, u itself would be equal to the square root of rho squared plus z squared. So u goes from 0 to a square root of a squared, square root of a squared plus z squared. Or this is equal to simply square root of a squared plus z squared minus z. So now over here, I can say that this integration right here, and let me erase this. This now becomes simply rho s v, therefore on the z-axis is going to be equal to rho s over 2 epsilon naught times square root of a squared plus z squared minus z. Y'all follow me on that, class? Now, as z goes to infinity, that goes to 0, by the way. Because as z goes to infinity, A squared plus Z squared is basically Z squared. Square root of that is just Z. Z minus Z is 0. So it does go to 0. Do you follow me? Now, how do I get the E field from that?
Be the negative.
Right, now I'm gonna say the E field on the Z-axis is minus the gradient of V, right? And there's only a Z variation, so it's gonna be minus the derivative of that with respect to Z, right? So it's minus rho S over 2 epsilon naught. And then when I take the derivative of the first term with respect to Z, what do I get? Well, it'd be 1 over, think about this. This is really A squared plus Z squared to the 1/2, right? So that boils down to 1/2, and it would be A squared plus Z squared to the 1/2 power times the derivative of this, which would be 2Z, right? And so it gets rid of that 2, and you put a Z there, and then it's minus 1 here, correct? All right, because the derivative of Z is just 1 with respect to Z, and it would be in the AZ direction. Now, that means the E field on the Z-axis, all right, would be equal to, well, the minus here, and we can interchange these things, and we can just put rho S over 2 epsilon naught, and then we can put 1 minus Z over A squared plus Z squared to the 1/2 power, AZ. I've got a point to make here. Do y'all agree with that? Now, here's the important thing. If you look at this, if A goes to infinity, wouldn't that really represent an infinite plane of charge? Y'all see this, class? Because there's a charge density rho S on that plate, but if the radius of that plate goes to infinity, then it looks like an infinite plane, right? Where does this go to? As A goes to infinity, that goes away, doesn't it? And you can see it goes to rho S over 2 epsilon naught, and that's exactly what we've calculated before, right? For an infinite plane. And in fact, it works. But this is a classic problem. This is the E field on the Z-axis for a plate with a constant charge density. I'll tell you a variant I do all the time. Instead of making it a constant charge density, I'll make the charge density a function of rho. And then I would give you the integration that you'd, like, I'd have several integrals in a table, and you would select the one that's appropriate. Do you follow me on this, class? But this is a good problem. I wanted to show you that. And that exposes how you first calculate the differential voltage, then the total voltage, and then take the gradient of the voltage with a minus sign to get the E field. And it's used all the time. All right. Now, the next thing, well, I'm going to talk about is current, or conduction current. Did you remember talking about conductivity in physics or resistivity, either one? All right, conductivity and resistivity are inverse relationships. It's like resistance and conductance. They both designate the same quantity, but one's the inverse of the other. Anyway, now we're going to talk about something. This is going to be current flowing. Current flowing. And we designate something called J. J is the current density, so this is current density. And that is equal to sigma E, and sigma is the conductivity. Its units are 1 over ohm meters or Siemens per meter. Conductivity is something that the larger its value, the better it is as a conductor. So for instance, the values of conductivity range from about 10 to the minus 14th to 10 to the minus 16th for insulators, all the way up to about 10 to the 8th for good conductors. And superconductors, it goes to infinity. But this is a normal range. Let me just say this. In the atmosphere right here that we're breathing, the conductivity of the air right here, if you put 2 plates of metal and you try to calculate the resistance between them, and there were very small distance between them, conductivity you'd use about 10 to the minus 14 to 10 to the minus 15, depending on the humidity. When you're talking about metals, This is the other extreme. Like silver, gold, you're talking about 5 times 10 to the minus, or I'm sorry, 5 times 10 to the 7th. Now, 10 to the 8th is an extreme, but I put it up there because that's like the upper limit. But you can see how many orders of magnitude of difference. You've got what? Really about 24 orders of magnitude that I'm showing you in difference. This is a huge, huge variation in the value of conductivity for different things. And that's important. Now, resistivity, the symbol for resistivity, the symbol is usually this, and this is why I don't like it. They usually show the exact row value that it's the symbol, same symbol we use for distance, is equal to 1 over conductivity. We stick with conductivity. They designate the same property. One's an inverse of the other. That's resistivity. And the resistivity is in ohm meters, by the way. So how is this important? I start out showing you how the value of conductivity in objects allows you to calculate the resistance between surfaces of that object. And I start out with a classic. I'm going to take a cylinder and fill it with a material. The material is going to have a conductivity sigma. This cylinder has a length L. It has a radius A. And I'm going to assume that the top surface here, the bottom surface and this surface here will all be metallized. And then I'm going to take a battery here with a voltage V. So you get a mental picture of what's going on. Now, in a battery, if that's conductivity is finite, it's going to cause current to leave the positive terminal, right? And it's going to flow back through the negative terminal, correct, class? Now, here's the way you use conductivity to calculate resistance. You have to assume something. You can either assume the voltage or the current. Usually, unless there's a really good reason not to, you start with the current. If I assume I, all right, I'm going to assume I. Now the next thing I'm going to get, so I'm assuming there's a certain current flowing here. Now, when I take a look at this, that current I'm assuming is uniformly distributed over the surface, and all the current is flowing this way. Do you agree with me then? All right, that means the current density, J, remember J's current density would just be what? I over the area, and if I call this the Z direction, then this would be equal to I over pi A squared AZ. A is just the cross-sectional area the current's flowing through. Do you all agree with that? Now, after that, from J, we get E. And E is equal to J divided by sigma, isn't it? I'm assuming sigma's constant through there. So that's equal to I over pi A squared sigma AZ. Now I have E. Agree with me? Now once I have E, I can get V. From E, I get V by saying it's the integral. And the nice thing about this, you don't need to worry about the sign, because the voltage we're going to get is a magnitude. It's a voltage difference between the two plates. You don't care about the sign, because the resistance we get is always positive. So now you go from, say, 0 to L. So I go from 0 to L, and I take the integral of E dot dl, which means it's the integral from 0 to L of I over pi A squared sigma AZ dot DZ AZ, or here I get a voltage V equal to simply I over pi A squared sigma times L. Does everybody follow me on that? I assumed I get J. After J, I get E. After E, I get V. I'm after resistance. That's really what conductivity is good for in terms of calculating things. So now I can calculate the resistance between these plates, R, and I can say it's just V over I, and you'll notice it becomes L over pi A squared sigma. You all see that? And that's the resistance. Now, a comment I'm gonna make here. This could be a square cross-sectional area. It could be a triangular cross-sectional area. As long as the cross-sectional area does not vary over the length of, whatever you want to call it, the resistor, resistance will always be for a constant cross-section. Remember, this is going to be a constant cross-section. It'll be proportional to the length, inversely proportional to cross-sectional area, and inversely proportional to sigma. That is resistance always if the conductivity is a constant and the cross-sectional area doesn't vary versus the length of the resistor. So remember, the only thing you care about is the area. You don't care about if it's an ellipse, if it's a circle, if it's a triangle, square, hexagon, it doesn't matter. And that's important. Now, here's a classic problem I like to do. Suppose you have a sphere with an inner radius A and an outer radius B, and it's filled with a conductivity sigma. And I drill a tiny little hole through here, so I can go ahead and I can put in a positive lead here, attach it to a battery, and then the outer shell is grounded. So I have plus to minus V here, and that means I'm gonna have a current I flowing. And then the current is gonna come out and it's gonna be radially distributed. You all see this, class? Think about it, you got an inner core, I run a little line in there, insulated, and I attach it to this inner core that's a radius A and metalize this whole inner core. And then I let current flow through it, and it's gonna come out radially. Do you agree with that? And it's gonna come to the outer surface and then return this way. So here's an interesting one. I assume I first, right? Now what's J? Well, do you all agree the current's radially outward? It's moving radially outward, right? So go out and put a distance R away and then draw a sphere there. All right? Remember, the same current flows from here, through all the surfaces of radius R. That current's constant, isn't it, class? So that means from there, my value of J would be equal to I over 4 pi R squared AR, right? This is R squared. This is the radius. Do you all agree with that? It's the total current divided by the surface area. What surface area? At any different distance R, there's a concentric spherical surface that's flowing through. So the value falls off of the current density is 1 over R squared, right? You agree with me? All right, now, if that's J, what's E? Class? J over sigma, right? So it's simply I over 4 pi sigma R squared AR, right? I'm after the resistance between the inner and outer cylindrical surface, correct? Now what's V? Remember, you don't have to worry about the sign, because it's always going to be a positive value of resistance. We're going to take voltage divided by current. What's V going to be?
Integral E dot dl.
Right, the integral of E dot dl, right? And in this case, it's going to be the integral of this, and I'll take the I over 4 pi sigma out in front, and then it's the integral of AR over R squared, times it's a differential length, right? And normally I could put down dr AR plus R d theta A theta plus R sine theta, or sine theta d phi A phi, and dot them, but I know that AR only dots into AR, so I can just dot with AR dr, and it's gonna go from A to B. You all see what I'm doing here? I integrate E field from the inner radius to the outer radius, right? And I don't care about the sign, I only care about the magnitude. Do you agree with me, class? Now what's this gonna be? Well, AR dot AR is 1. What's the integral of 1 over R squared? 2. Minus 1 over R, isn't it, class? So then when I evaluate this, I get V equal to I over 4 pi sigma And then it's gonna be, this will integrate to 1 over R, 1 over A minus 1 over B. And I changed the order because A is assumed less than B, and the magnitude, technically you would put a minus sign here, but this is the value. Do you follow me? Now, if that's the voltage, what's the resistance? Just divide this by I, right? And if I divide that by I, you can see that in fact, it's this. So that's another way to get resistance for, now we have concentric spheres. Obviously, the concentric cylinders could be, you could use that too, couldn't you, class? I could have an inner radius A, outer radius B for a certain height cylinder, calculate resistance between that, okay? All right, now I gotta give you your quiz. So, would you do me a favor? Put at least one desk